In our last lesson, we took a look at what a chemical equilibrium was and how we could calculate an equilibrium constant. This allowed us to know whether or not when a reaction occurred, the equilibrium would lie where we had many products or many reactants. leChatelier was a scientist who wanted to try to figure out how we could make reactions move to favor the products or reactants according to how we wanted to do it. His principle basically says that the harder you try to do something, the faster it will be undone. Henri leChatelier says that if a system is at equilibrium and you do something to mess up the equilibrium, we call that a stress. If we make it unhappy by giving it stress, it's going to do everything in its power to get back to its happy place, to be unstressed again. The general idea is that whatever we do to stress the system will try to undo. And in that, we are able to actually push reactions around to make more products or more reactants as we see fit. If a system is at equilibrium and we apply a stress, it always shifts to restore the original conditions. There are 3 stresses that we can actually apply to affect an equilibrium. We can change the concentration of either the reactants or the products. We can affect the pressure if the system is gaseous, and we do that by changing the volume. And we can change the temperature. By affecting these 3 stresses, we can actually cause the position that the equilibrium occurs in to move so that we produce more products or more reactants as we would choose. So we're going to look at each of these stresses separately and see if we can predict the effect that the stress will have. Let's start with concentration. The first thing I need you to know is that when we change the concentration, this will not change the KEQ. The KEQ stays the same, and that's important because it allows us to make more products or reactants as we would need. So we're going to consider a really simple reaction where we've got 2 reactants, A and B, and they're going to react to make a single product called C. Now, if we increase A, if my stress is to increase A, I'm going to add more of it. I'll put more A into the reaction chamber. The system wants to undo the stress. The opposite of adding more of something is to remove it. And so the only way to remove that excess A is to react it with B. In other words, the system is going to follow the forward direction reaction. It's going to take this excess A, it's going to use some of the B, and it's going to make more C. Now the result of that is the amount of B will go down, it's going to get used up, and the amount of C will increase. As I continue to explain and show you examples, I'm going to do my stress in red and the effect of that stress in green. So we're going to use this idea to see what would happen if I added more A or more C, and what would happen if I decreased A or C, because we can increase or decrease reactants of products, or concentrations of products and reactants. So in our analogy, I'm going to make my A's in red, my B's in blue, and my C will be a combination. So if I'm at equilibrium as this stands, and as this stands, we are seeing that we're in a situation where we've got 2 A's, I see 2 B's and 1 C. If this is indeed equilibrium, every time an A and a B react, another one breaks down. I'm at 2 to 2 to 1. If another one reacts, then another one breaks down. I'm at 2 to 2 to 1. My KEQ is now 1 over 2 times 2, or 0.25. It's holding steady. It doesn't matter where the equilibrium sits. I've just decided that this is going to be its position. What if I add more A? So here's my stress. My stress is to increase the amount of A. So I'm going to put another A into the pot. Now the system doesn't want it. My stress was to add A. The system wants to get rid of A, but it doesn't have hands. It can't reach in and throw that out. All it can do is follow either the forward or the reverse reaction. So in order to get rid of this excess A, what it has to do is react it with a B. I've now restored A back to 2. It's back to where it was. But what is the effect of this stress? Well, the effect is now I have less B. The effect is that the amount of B went down, and I'm going to have more C. We followed the forward reaction, and we would call this a shift to the right. When we add a reactant, we shift towards the products to use that excess reactant. Now, my amounts here aren't very accurate because what I've essentially done is increased my A and B, which is my denominator in my KEQ expression. And so in order to keep the KEQ constant, C has to increase somewhat and my denominator has to go back down somewhat in order to keep it the same. But pictorially, we can see what's happening. All right, what would happen if I increase C? All right, I've reset the original conditions. Again, we're assuming that we're at an equilibrium. So every time that we have one product made, one breaks down, and we end up with that 2 to 2 to 1 scenario. What if I increase C? Well, to increase C, that means I'm going to put another combination in. So my stress was to increase C. I've got another one of the products there. The system wants to do the opposite. The opposite of me putting C into the pot is taking C out of the pot. But again, this is a chemical reaction. It doesn't have hands. It can't just reach in and throw it away. So it has to follow either the forward or the reverse reaction. To get rid of this excess C, it can break it down. It can take one of those C's and following the reverse reaction, it can break it down to form an A and a B. Well, look at what's happened as a result. I have more A and I have more B. That excess C is now gone. I've restored the original amount. So the stress was to increase C. The effect of the stress was that A and B increased. In this case, we had a shift to the left. We followed the reverse reaction to get rid of the excess addition of one of the products. What happens if we remove and lower the concentrations? All right, in this case, what I'm going to do is stress this by removing A. So I'm going to pick up an A and take it out. The opposite of removing A is putting it back. In order to replace that missing A, we have to follow the reverse reaction and break down a C. We're back to having 2 A's. I have followed the reverse reaction. The result is we now have 3 B's, the amount has gone up, and the amount of C's has gone down. Again, the shift is to the left. Finally, we asked what happens if I remove C, if I lower the concentration of C. Okay, here goes one of the C's, off it goes. The system wants to put it back. Only in the forward direction do we make more C to put it back. So in the forward reaction, A and a B will react together to make a C. This has had the result of lowering the amount of A and B in the pot. We've driven the reaction forward. We shifted to the right. So we can see that whatever we do, the system immediately shifts left or right. It follows the reverse or the forward reaction in order to undo. What effect does pressure have? Again, pressure has no effect on the KEQ. Pressure is only going to be important if we're working with gases. Solids and liquids aren't considered to put pressure on a container because they're not really hitting the walls of the container with enough force to be noticed. Only a gas with its random elastic collisions puts pressure on the walls of a container. So we know that whatever we do, the system wants to undo. If we increase the pressure, the system wants to decrease it. I can increase the pressure by, for example, decreasing the volume. In this example that we see here, we've taken this plunger and pushed it down, so I've got the same amount of particles in a smaller place. So by decreasing the volume, I've had the effect of increasing the pressure. Now, I point this out because questions are often going to talk about volume and pressure separately, but remember they're opposite to each other. we need to think in terms of pressure. If I increase pressure, the system wants to decrease it. I've pushed down on this plunger, I've increased the pressure, it wants to take the pressure off, but the system can't push the plunger back up. So what is it going to do? Well, the only way to get less pressure is to get less moles of gas hitting the walls of the container. And in order to do that, we need to look at our equation and say, where is there less moles of gas? On the reactant side, we have 2 moles of gas. On the product side, we have 1 mole of gas. Moving in the forward direction actually reduces the amount of moles of gas and therefore causes less pressure on the container. Let's take a look at this in terms of the same graphic we were just using. So again, I've set this up as an equilibrium where 2 A's and 2 B's are reacting to make 1 C, and I've decided this is going to be my equilibrium position. So again, this reaction continues every time one product's made, another one breaks down to reform reactants. So the numbers stay constant. If we take a look at this situation, you'll notice that there are 5 particles here. We've got 1, 2, 3, 4, 5 particles of gas putting pressure on this container. And we know that it's putting pressure because these things are all bouncing around in the container. They're hitting the walls, and that's what's causing the pressure. So if I now take a plunger and I put a big cap on this and push this down, these 5 particles are in a smaller space. My volume's gone down, so my pressure has gone up. And the system says, hey, I don't like this extra pressure. How can I get less pressure inside this container? And the answer is I need less particles. If less things hit the wall of the container, there will be less pressure. So I'm going to get less particles by moving in the forward direction. You can see that if I take an A and a B and react them together, okay, I now have 1, 2, 3, 4 particles. 4 particles puts less pressure than 5 particles. So by moving forward, by following the forward arrow here, I have actually created less pressure and undid the stress. Now the effect of that is I've got more of my products, but I have less of my reactants. What if I now want to give this more space and reduce the pressure? So suppose now I reduce the pressure. I take the lid off this container, or I put it in a much larger container. Right now there was 5 particles of gas putting pressure on the walls of the container, and sorry, I'm not reducing the pressure, I'm increasing the pressure. Let's make sure I'm saying this correctly here. Nope, never mind, I had it right the first time. I'm reducing the pressure. So I have now reduced the pressure. The system goes, if this is my stress was to reduce the pressure, what does the system want to do? Well, the opposite of the stress. The system wants to increase the pressure. It wants to put it back. And the only way it can do that is it has to make more particles of gas. It has to make more moles of gas. And which way does it do that? Well, it does that by following the reverse reaction. Because right now I see 5 particles of gas, but if I follow the reverse reaction and break down another C, I now have 1, 2, 3, 4, 5, 6. I now have created 6 particles, and that would make more particles hitting the walls of the container and would make more pressure. So first we go, what is the stress? Then we have to think, how do I undo that stress, and which way will do that? So we're going to follow the reverse reaction. That means I get more of both A and B and less of my C. So the effect of the system reestablishing the equilibrium is what we're looking for. Our final stress that we can apply is temperature. And temperature is the only thing that actually changes the system's equilibrium constant. In fact, most of the time when you see a KEQ given in text, they'll say this is the KEQ at this temperature, because all equilibria are temperature dependent. The same rule applies. Whatever we do, the system will try to undo. If I heat it up, it's going to try to cool off. If I cool it down, it's going to try to heat up. So in order to know what's going to happen, we have to know if the system is endo or exothermic. Now, if the system is endothermic, then the word heat will always be written on the left. Heat is going into it. And we'll notice that the delta H is positive. So if I see a positive delta H, that could be a clue that they could tell me it's an endothermic reaction. Or if I see that my reactants plus heat, sometimes they'll put the word heat right in the equation, then I know it's an endothermic reaction. If a reaction is exothermic, then the heat is going to be given off as a product. Heat is being generated, it's being produced. So I write it on the right-hand side of the arrow. And my clue that they might give me is a negative in terms of value of delta H. But what's really important to me is to know which side of the equation do I write the word heat on, because that allows me to predict the direction that the equilibrium will shift. Let's pretend for a minute that my initial equation here is endothermic. So if it's endothermic, heat goes into the reaction as a reactant. So A and B are going to react with the heat to make C. If I now go and I heat this entire reaction chamber up, I put a fire under it and I warm it up, the system wants to cool off. If a system is going to want to cool off, it's going to want to not move towards the heat. If I move in this direction, I'm moving towards the word heat. That's producing heat, so that won't happen. If, however, I move in this direction, we know the heat gets used up with the A and the B when it forms C. In the forward direction, when I move this way, what we can see happening is A and B react to make C. So the amount of C's will increase. The amount of A and B will decrease, as will the heat. That'll cool the system back off. Now, if the system were instead to be exothermic and was producing heat, okay, we'll reset the original conditions here. And we know the system produces heat. If I now heat the system up and it wants to cool off, it wants to get rid of this extra heat that I'm putting in here, again, it's going to move away from the word heat. You can't move it towards the fire to cool down. So away from the word heat is this way, which means that we're breaking apart the reactants. That's what's happening. C is breaking apart to form A and B. And so the amount of A and B is going up and the amount of C is going down. The effect of that stress is to increase the amount of the reactants. So we can actually use this to figure out which way the reaction is going to move in response to the stress. In order to practice the equilibrium reactions and equilibrium shifting according to leChatelier's principle, I'd like you to start with your workbook that has a large equation, and they're going to give you the stress and ask you to predict the effect of that stress. There's also questions in chapter 17 of your textbook. Now, you may choose to do this right away, or you may choose to watch my next video in this series on leChatelier, where I look at the Haber-Bosch process and how we can cause that particular reaction to go in a way that is economically viable.